Just today we'll discuss about the limit of a complex function. Okay, what is the limit of a complex function? So just you can see f of x be a function fj. Complex function already we have known that there is the one real part and one imaginary part is available there. So first of all, you choose f of x. F of x. That is a function. F of x be a function. And just to need to find the limit of that function. Then we can say that z tends to z0. Z approaches to z0. Z approaches to z0 of a function. That is the limit. But when considered there is the two functions f of j minus of L, limiting him to L, which is equal to epsilon, less than equal to epsilon. For another condition, z minus z0 mod is less than delta. Just you can see two things. F of z minus L is less than epsilon, or z minus z0 is less than delta. There are the two neighborhood points epsilon and delta, because both are approaches. Just this is one the delta, and center is z0. Delta center is z0, and this is epsilon, and this is delta, and this is epsilon, and this is L. Center is L. There are two separate figures in the function f of z minus L less than epsilon, or z minus z0 is less than delta. For every z is not equal to z0, z is not equal to z0. This z is not equal to z0. For every z is not equal to z0 in the delta case, in this case, for every z is not equal to z0 in this delta case of z plane. This is z plane. But as a value laying the epsilon days, the value laying in the epsilon days, that is f of z in the omega plane. The functional value of j, which laying in the epsilon or second plane, that is omega plane. Just to look out here, the value of functional value of j which laying in the function of z, and that is in the omega plane. And just in saying that limit z tends to z0 of f of z which is equal to L. This is the limiting value. Limit z tends to z0 into f of z is equal to L. That is the limiting value of the given function. The definition of the limit for the similar that ordinary calculus is quite different for the real calculus. This is totally real different calculation of this class. So continuity of a function omega is equal to f of z is a continuous. This function f of z is equal to omega, that is the continuous function at the point of z0. Because this is continuous function, so this one is also continuous function at the point of z0. So that you can say that omega a function f of z is a continuous function at the point of z is equal to z0. If limit z tends to z0 is equal to f of z, we can say that f of z function is continuous. We can say here f of z is continuous function. F of z is said to be continuous. Said to be continuous. that is the omega. For which condition this one is satisfied for a continuous function? Now, if limit z tends to 0, f of z f or that is f of z 0, then it is continuous function. Further, f of z said to be continuous in the region R of the z plane. F of z is also a continuous function in the z plane. This one is also continuous function in the z plane. If it continues at every point of that region, f of z is continuous at the z plane if it is continuous at every point of the z plane. So this is the limiting rate. So just you remember what is complex function and what is real function. Complex function is basically considered of x and y, two variables or two coordinate axis systems. But in the case of real numbers, that is one-dimensional cases. So when it is said to be continuous, so that is two criteria given. When this is the f of z minus L mod is less than epsilon, or z minus z is less than epsilon. What epsilon delta are the neighborhood points? Neighborhood points, that means that is the nearest points, nearest and equal point. If this condition is satisfied, then this condition is also satisfied. So this is the limit point which exists. If limit point is exist, how to calculate limit point is exist? Then how to calculate the derivative of the function f of derivative of the function f of z? How to calculate derivative? Derivative of the function. We have already known that function f of z, and that is omega we have to mention here. When we can find the derivative of this function, complex function, just we can write d omega by dz. D omega by dz. That is also represented as this. And that is also related by the concept limit z tends to z0. F z plus delta z minus f of z by delta z. Provided that the limit exists and has the same value of different ways in which the delta z approaches to 0. Limit is exist. Mostly limit is exist, then you can find the derivative. If limit is exist, then you can find the derivative of the function. Just you can look out from this figure, just to consider a point P, and that is a point xy. P is a point that we are considering historically. P is a point of xy. Is fixed, and Q is another point, and that is z plus del z. This is a one point increased by x, then x plus del x is increased, y is fixed, and that is also another point, y is increased, x is constant, y plus del y. So this is increased by x, y, and this is increased by x, and this is put the value of x del x comma y del y. Just to recall here, this is the points. नेमिंग करेंगे तो क्या होगा? P and Q, this is the point of Q, and this is the region R. The point Q may approaches P along any straight, or per path of the given region. P approaches to Q either straight or per path to reach the point of Q. So how to reach this value? Now P approaches to Q. Very different process. What are the process? P along any straight P along any straight Q may approach another way curve structure also. Delta may tend to zero in any manner or curve manner, straight or curve manner, P along curve manner. This is to approach to zero of this point, either straight line or vertical straight curve, but tends to zero. Any point that point to be substituted we get meet the point. Delta Z tend to zero at any value. dw delta may not exist, may exist, may not exist. If therefore becomes a fundamental problem to determine the necessary and sufficient conditions of dw by dz to exist. For existence of dw by dz, we need to show the existence criteria. What is the existence criteria? That is the necessary and sufficient condition. Necessary and sufficient condition for the derivative of the functions of omega. So it is very much essential to evaluate the necessary and sufficient conditions for existence of the derivative of the complex plane. So what is the necessary and sufficient condition? Necessary and sufficient condition. So just we leave out the necessary and sufficient condition. The necessary and sufficient conditions for the derivative, consider omega is equal to f of z is equal to q of x comma y plus I into p of x. This one the function you consider. The necessary and sufficient conditions are for the derivative of this function. The necessary and sufficient conditions. Necessary and sufficient conditions. Sufficient conditions. What is the necessary and sufficient conditions of omega equal to f of z? It exists all values of z. Exist all values of z. All values of z. It is exists for all values of z in a region R. In a region R. What is the necessary conditions? The first two conditions are there. What are the two conditions? The first conditions, all derivative, del u by del x, del u by del y, del p by del x, del p by del y are continuous functions of x and y. are continuous functions of x and y. Del u by del x, del u by del y, del v by del x, del v by del y are the continuous functions of x and y. Of function in R. This is first condition. What is second condition? Del u by del x is equal to del v by del y. This equation to del v by del y. First and last relation. Del u by del x is equal to del v by del y. Del u by del y is equal to minus del v by del x. Del u by del y is equal to minus of del v by del x. This condition is satisfied. This relation is also called as the Cauchy-Riemann relation or Cauchy-Riemann equation. This relation is basically called as the Cauchy-Riemann equation. So first we can see the necessary conditions for the existence of the derivative of f of z is that CR equation should be satisfied. If CR equation is satisfied, then it is the necessary condition. This CR equation is satisfied. तो क्या हुआ? CR equation satisfy करेगा. A necessary condition for existence. The necessary satisfied, then necessary conditions for existence. This is necessary condition for existence is there if its CR equation is satisfied. Sufficient conditions. First one is sufficient conditions. Del u by del x, del u by del y, del u by del x, del u by del y, del v by del x, del v by del y. Is a single valued function possessing partial derivatives at each point consists the partial derivatives for f of z. Consist the partial derivatives of the function f of x, f of z. If partial derivatives value are consist of the function f of z, then this condition is called as the sufficient condition. This is sufficient condition. Sufficient condition. So del u by del x, del u by del y, del v by del x, del v by del y consist of the partial derivative, and these are called the sufficient conditions of the complex plane. The next will come just analytic functions. Analytic functions. So anybody can, what is the meaning of the analytic function? A function f of z which is a single valued function. F of z is a function that is a single valued function. Single valued function. F of z is a single valued function and possesses a unique derivatives with respect to z. Possesses unique derivative. Unique derivative with respect to z at all points of the region R. All points in the region R. Analytic functions basically defined here as a single valued function possesses the unique derivative with respect to z at all points in the region R is called as analytic functions. This is called as the analytic function. Analytic functions are also called as the regular functions or holomorphic functions. Analytic functions. These functions, analytic functions is also called as the regular functions. Regular functions. So analytic functions also we say that is the regular functions or holomorphic functions. Morphic functions. So define analytic functions. The author name of the analytic functions also explained here. A function which is analytic everywhere in the complex plane is known as the entire function. This is only described here of the complex plane. This one is described only for the complex plane. So, what is analytic functions? But this is a single valued function that object possesses the unit derivative for all z. Derivative respect to z at all points in the region. That is called as the analytic functions. The analytic functions is also called as the regular functions or holomorphic functions. The entire functions also there. We can also say that a function which is analytic everywhere in the complex plane. This is a complex plane. Then f of z. This is an analytic functions. Complex plane. A function f of z is analytic everywhere. Analytic everywhere. In the complex plane. Complex plane is known as the entire functions, and that is termed as the entire functions. Just remember, analytic function f of z is analytic everywhere in the complex plane, and that is known as the entire functions. As derivative of a polynomial exists at every point, a polynomial of any degree is an entire function. For one example, we consider for the entire function. Polynomial Ex be a polynomial. Ex be a polynomial. Derivative of polynomial exists. Derivative of polynomial. Derivative means p dash x of a polynomial exists at every point at every point. Derivative of a polynomial exists at every point. Derivative of a polynomial exists at every point. Any bracket. A polynomial of any degree is an entire function. Polynomial of any degree at any degree is an entire function. Any degree of the polynomial which must be the entire function. A point at which an analytic function suggests to possesses the derivative is called singular point. Derivative of the singular point seized is called as the singular point. A point at which the analytic function seizes. A point at which the singular analytic function is seizes, and that is called as the singular point. Point at which a point at which an analytic function seizes. Called as the singular point. This is the concept, and this is called as the singular point. Omega log z, that is non-analytic. Omega is a log z function that is not analytic function because it does not satisfy the particular equations. So first one example we need to show that if a function is analytic and to determine find the LW at z and derivative where u is the non-analytic function, omega is the non-analytic function. One function omega is equal to f of z. Just you can see omega is equal to f of z is equal to log z. That is the one question. If omega by dz you can need to find, and determine where omega is non-analytic. Omega is non-analytic. you need to check this function. Determine this is not. So this one is the question is that omega is equal to f of z is equal to log of z is there. So first of all, you choose here u is equal to omega is equal to u plus of I e, and that value you represent log z, log x plus of I y, and this value becomes 1 by 2 log x square plus y square, is the real part, and plus I into tan of y by x. This makes sense. And you can check here u, this is the value, this part is u, and this part is e. Then del u by del x, del u by del x, that is also x by x square plus y square value is there, and del p by del y, which is same as the del p by del y. You can check this value. And del u by del y, del u by del y, which is equal to y by x square plus y square, and which is same as the value minus del p by del x. Then this equation is satisfied with Cauchy-Riemann equations. That means derivatives exist. If Cauchy-Riemann equations satisfy, it is the necessary conditions or sufficient conditions. Necessary conditions is satisfied. Here equation satisfy means that is the necessary conditions for the existence of the complex plane is satisfied. Hence, Cauchy-Riemann equation satisfied here. But partial derivatives are continuous except at the zero. Partial derivatives are continuous except at zero. At the point of zero, this function is not defined. This function also not defined at the origin. Except zero, partial derivatives are continuous. Except zero, except origin, omega is continuous, or partial derivative is continuous. Except zero, partial derivatives are continuous. Hence, omega is analytic everywhere except zero. Hence, omega is continuous everywhere except zero. Omega is continuous everywhere except zero. Okay. So we discuss next.